Today, we're going to be taking a semi-in-depth look at my 6502 breadboard computer in order to understand what it is, what it does, and how it was made. So, we'll start with a little background and a little disclaimer. If you don't like listening to a nerd rant about obscure technology, this might not be the video for you. But if you do, please stick around. So, where did this project begin? So officially, this project began in 2017. The project had a few goals in mind. I wanted to build a 6502 breadboard computer. I wanted to write all of the software for it, which I mostly did. And I wanted to make it with readily available 6502 components that you can still buy brand new. In the case of the current incarnation of this board, there are not strictly brand new components on it, but they can be substituted with brand new components where need be. I just have the older ones on because that's what I had on hand when certain chips failed. This whole thing stemmed from a love of 6502 based computers, having collected quite a few vintage computers myself. In short, I wanted to recreate the look and feel of a vintage computer with modern components and challenge myself to code in a way that I had never coded before. So, let's take a look at the board itself and figure out what we have. We'll start with a basic board layout. I won't go over every little component here, but just the key players. Starting here, we have a 65C02 processor, which is just the CMOS version of the 6502 processor. This also did have some added advantages for programming that allowed me to write my monitor in the way that it is. So I would not be able to use my monitor on a regular non-CMOS version. Moving to the left, we have, under all of these wires, you can probably see it under there, there is a RAM chip. This RAM chip is 32 kilobytes, but with the way that the address decoding works, which we'll get to in a second, it only gives you 16 kilobytes of RAM. More than enough for my use. On the left here, we have a 32 kilobyte ROM chip. With the address decoding, we get the full 32K. This is important to me, so I have plenty of space to store programs that I write on an assembler. Moving right along, we have a 6551 ACIA chip, which is just a serial input-output chip. Next to that is a 6522 VIA, or Versatile Interface Adapter, which is 8-bit parallel, and it has 2 ports. This gives us general-purpose input and output, and there's 2 of these on board. Moving over, there's some clock generation, which is done with a 555 timer, I believe. It's been a while since I've worked on this. And some 7/4 logic, which is used for the address decoding. Now, the address decoding I got from the 6502 primer, which was written by Garth Wilson. It's a lovely little resource which is used for anybody looking to do their own homebrew 6502 computer. And address decoding is one of the most important things, as it determines the location in memory of everything on the board. So, I cannot thank him enough for having done that. Moving right along, we have another one of these versatile interface adapter chips that I was talking about. Some clock crystals, which are used for the sound chip and the serial chip. And I'll get to the sound chip in a second. You notice a YM2612, which has not been hooked up yet, but that's something I'm working on. But the star of the show, sound-wise, is an SN76489 sound chip. This has 3 square wave channels and 1 noise channel, and was used on things like the Texas Instruments 994A and the BBC Micro. Moving along, we have an Atmel controller. Specifically, an ATtiny26. There's a lovely write-up by somebody by the name of Daryl Richter, who shows a way that you can use this Atmel controller to make a keyboard interface for a 6502 computer. It's able to decode signals from a PS2 computer into 8-bit parallel ASCII data. There are also handshake lines, which I'm using a bit differently than is mentioned in the write-up. Essentially, the handshake lines I have tied together, which means when the Atmel controller says that it has a byte available, it will trigger one of its lines. And it has a handshake line where it's expecting a response back to say, okay, we got the character. Well, if you tie those two together, what happens is the Atmel controller signifies that there is a byte of ASCII data that the computer needs, but it immediately triggers its own line that answers. So what that does is creates a momentary ground pulse. So using one of the VIAs, I just am detecting that ground pulse. So that way, there's no need for handshaking in my monitor. It just says, if there's a ground pulse on this one single control line that I've combined, that's how we'll know to check the chip for data. I hope that makes sense. And finally, we have a character LCD. These things are used in so many different things, but it's one of the display methods that I have. And speaking of display methods, on the end, we have something called a telemate tiny, which is made by BatSox. This is the primary display method, and essentially, it's just a terminal whose output is a composite output. So you can plug it into any TV. So the serial chip sends it its data, and the telemate tiny is responsible for displaying said data. Now you know what the board does, what it has on it. Let's take a look at the display methods and the software that I have loaded on it. A brief note before we start. I just wanted to note how the peripherals were connected. There's 4 parallel ports from the 2 VIA chips, and I believe I have room for 1 more so that I can have 2 unused I/O ports. But on the VIA chip, we have the sound chip, the LCD display, the keyboard lines, and the control lines for the sound chip and the keyboard. Just basically anything control that needs to be done. So, I'm going to power this on, and the first thing we'll hear is the sound chip. Having no data, it's just going to play a random tone. I'll reset, which will play a beep and clear the sound chip. And then we should get a splash screen. And there we see revision 3.0, dated today, actually, September 10th, 2021. In preparation for this video, I made revision 3 of this monitor, which has a couple of added benefits, and we'll go over what this monitor does. This is a basic operating system that I wrote, and as a memory monitor, it does all the things you'd expect a memory monitor to do. It can read addresses and get you the memory contents at that address. We can write data to memory addresses. We can run code, and a couple of other things. So let's take a look. First things first, I'm going to type in an address. We'll do 2000, which is just an address in RAM, and hit enter. It returns a data byte for me. So 6A is what's at 2000. And I can do this for anything. For example, my reset vector. Now, the screen, as we might see, scrolls infinitely. But if I want to clear it out, I've added this little clear command, which clears the screen out. It just sends some ASCII characters that tell the telemate tiny to clear the screen. And it is smart enough to tell the difference between a C. Oh, sorry, messed up there. It's smart enough to know the difference between a C in an address and a C in clear. So we can read, we can clear the screen. Let's write. So if I type in write, and then I want to write at 2000, what do I want to write? I will write 00 at 2000. When I hit enter, we get OK. So it lets me know that that has been done. And we know it's been done because if I read 2000, we see the data byte there that I just put. So I'm going to clear out, and we're going to do that again to show you how you might enter code on this system. Do one write command like this, and then from here, if we type a space, this is going to tell my monitor to write this data byte to the next address. So that way I don't have to sit there and retype in the write command every time. So I can do this, and it should just be writing to each memory address, each subsequent memory address. So let me clear out, and we can see that it worked, because if I read back sequential addresses, all that data is there. But reading addresses one at a time is kind of a pain. So I've made a list command. Now I believe the Apple I monitor had something like this, and it looked exactly the same. Granted, I did this coding myself, so I don't know how they did it. I'm just doing it this way. I'm going to type in L for list, and the addresses that I want to list. This is the max amount that it can show on the screen without overflowing. So if I hit enter, it's going to show me the data, and we can see all the data that I put in. And we also have address markers to let us know where we're looking at. So 2000 starts with 2000, 2001, 2, 3, 4, 5, 6, 7. And then 2008, 8, 9, A, B, C, D, E, F, and so on and so forth. So that's pretty useful. Like, if I wanted to look at what is happening in ROM, at least the start of it, there we go. So I don't have to do that one at a time. Now, as I've said, we can run software, and that's super important. My monitor starts at 8,000, so we can test that this works. If I tell it run 8,000, it restarts the monitor. Pretty neat. But we have some other software. First things first, at 8600, so we have this program, SimTerm, that I wrote. It is a simple terminal program. Using an FTDI breakout board, the serial chip on this computer will send out whatever I type to a modem or a breakout board, and I can actually surf bulletin boards with it. We'll come back to this and actually do that. Now, you can see that the display reinitialized, and if I exit by pressing AND, it's going to reinitialize again. And that is because the serial chip drives the display, and in monitor it runs at 19.2K, and for SimTerm it runs at 1200 baud. So if I change the program, it's going to have to reinitialize the display to work at the slower baud rate, which it does do. Okay, the switch has been made to terminal mode. As you can see, I can issue modem commands, and I get one back. So I'm just going to send it to Heatwave, which is a bulletin board system I used to get on. And you can see we actually have functioning bulletin board capability on this computer. And I don't remember my user information, so I'm going to hit search. All right, we're back. I found my user ID. Had to scroll down a little bit because it had my city and state in there, and obviously I don't want to, relay that to the world. The problem is that a lot of these work at 40 columns, and this Telemate Tiny I think only does 32. There are some ways around that, but it's no big deal. I'm just going to log off anyway, but just to show you that it works, so I'll hit G for goodbye. Yes, I want to log off. And it's going to do some cool little things here. Well, it says heat. You can't see the wave part. And so that's done. The other thing, as any computer from the era would want to do, we have BASIC. I'm running Lee Davison's EhBasic. I'm running his EhBasic, which is a 6502 BASIC that can basically run on any system. The end user's responsibility is to make input and output routines for the display and load and save routines if you want them. So I did that. And if I run, it's asking me if I want a cold or a warm start. I'm going to do cold. For memory size, I'm just going to leave it blank and hit enter, and it will count the available memory. So I've allotted about 14K for BASIC, which is most of the memory that we have. And as a basic program interpreter would expect, I can type in your regular commands. I'm not going to do an infinite loop because breaking commands in this version of BASIC has proved to be very hard for me. But I'm just going to make something that repeats 50 times. And if I type in list, we can see there's my program. I don't know why it listed that way. That's weird. I'm going to just retype that. It might have just been some weirdness with the way that I was typing. Yeah, that's exactly what it was. Something I did, put it in as 1. Could just be because I messed up with the backspace and stuff. No big deal though. There it is. And if I run, it does it. And if I list, like I said, there's my program. And we can do anything that you might expect. So what I'll do instead now is tell it to ask me to put something in. So now our program looks like that. We're going to input a variable and then print it 50 times. So there it is. And then, finally, I'm going to reset. Okay, we're back with the VGM player in RAM, or on ROM, excuse me. And before we play the song, the first thing that I have to do is figure out why my keyboard's not putting anything into the system. There we go. So what I have to do is write in RAM at 2000, we're going to write 01. That data byte in RAM at that address controls the speed of the song playing. So I have it 01, which is the fastest we can set it to. And that should be full speed. So now if I run it 8600, it's going to play a VGM file, which should be from a Sonic game. Works pretty well. And if I go to reset it, it'll hang. There's a little bit of a delay with the capture card, but it does work. So let's see how the speed works. If I write 02 to it, the song should now be a little slower. And it hung up there, unfortunately. There's just the stability issues right now. And let's write it even slower. So it's pretty cool what you can do with this computer, and once I fix its stability issues, this should be a pretty reliable and fun hobbyist system, and eventually I might put it on PCB, and if I do, I might provide those files as a kit for you to buy if you'd like it to make yourself. Not for me to sell to you, just for you to buy the board and have it fabricated, so on and so forth. Anyway, I hope you've enjoyed this video, and we'll do more things like this in the future.